Hello. In this video, I'm going to solve an ideal Rankine cycle problem. The Rankine cycle is the model behind steam power plant or any vapor power plant for that matter. In this problem, the turbine inlet condition, state 1, is completely supplied along with the mass flow rate of the steam flowing through this cycle. Also supplied is the condenser pressure. We are also asked to find not only the thermal efficiency but to do a what-if study on how the efficiency will be affected if the condenser pressure is changed. I have already logged in as a student. We launch the suitable test step, which would be obviously to the specific branch, and you can see vapor power and steam and gas power are handled in this module. Out of different material models, we'll select the PC model because there is possibility of phase change. And we click on HTML5 to launch the test step. The default state is already state 1 with H2O being the default fluid. So therefore, this is perfect for turbine inlet state, which is given, the information given is 4 MPa is the inlet pressure. And the temperature, we click on temperature to turn it into an input mode, is 800 Celsius. Mass flow rate is given is 10 kg per second, therefore the state can be calculated. State 2 is the turbine exit or the condenser inlet, so the pressure must be 10 kPa and it's an isentropic turbine, therefore entropy must be constant throughout the turbine and mass flow rate is obviously not changing. So state 2 is calculated. To save time, I have already calculated state 3, which is the condenser exit. Pressure doesn't drop and quality is 0 to make the liquid saturated liquid. The H2O is saturated liquid in an ideal Rankine cycle at the condenser exit. Mass flow rate is the same. And then from state 3, the fluid is pumped up to state 4, and in a pump, isentropic pump, the entropy remains constant. As you can see, S4 equals S3. Again, the pressure must be at the end of the pump same as the turbine inlet pressure or the boiler pressure. Mass flow rate is the same. So therefore, all the states have been calculated. Well, now that we have calculated all the 4 states, let's go to the graphics panel to make sure they make sense. 1, 2 is the turbine, 2 to 3 is the condenser, and 3 to 4 is on top of each other. That's why the reason is that the entropy remains constant in a pump which handles a liquid. For a liquid, entropy is a function of temperature alone. So that's why state 3 and 4 on a TS diagram are on top of each other. If this was a TV diagram, there would be a slight separation, for example. So the states looks correct. Let's go to the device panel. Device 1 is our turbine. State 1 is the turbine inlet state. And state 2 is the turbine exit state. There is no heat transfer in an adiabatic ideal turbine. We calculate the turbine output. I have done the same to save time for the condenser, where state 2 is the inlet and state 3 is the exit. There is no work and heat transfer is calculated. And then the pump. Again, the inlet and exit conditions are first loaded, and then there is no heat transfer, so work is calculated. And finally, for the boiler, it takes steam from state 4 to state 1, and the heat transfer is calculated. So with all the devices done, the cycle must be ready. It's complete as shown here. First thing to check is that Q.net must be equal W.net. That's the consistency of calculation. And the efficiency is found as 41.78%. Now to do the what-if study, let me show you an interesting thing. We can go to the I/O panel and declare a variable P condenser or PCOND equals 10. All the variable must be in SI units. The calculated, so this variable is now recorded. P condenser is 10. We can go back to the state panel. The only place the condenser pressure was entered was state 2, if you recall. So instead of a fixed variable, we can just go and change it to equals P condenser. So now if we calculate the state, we put the pointer over P condenser, you will see its value show up in this top panel, which says that P2 equals P condenser equals 10 kPa. Of course, if I do a super calculate that updates all calculations and produces test codes, you go to the cycle panel, the efficiency is still the same, nothing has changed. Let's go back to the user code, and now suppose we change efficiency, condenser pressure to, let's say, 20 kPa. To record the change, we click calculate, and then super calculate to update all calculations, and go to the cycle panel. The new efficiency you can see is now 38.81%, 39.81%. So the efficiency has dropped. So you can see the power of using variables in the I/O panel. You can declare all the major variables here and later can change them and see their effect on the entire cycle.